Okay. The second session is about what I prepared before. To build an entire SNARK, a minimal mini SNARK from Sumcheck. There will be some math, but it's okay. So if you have any question, please interrupt me. I will appreciate that asking more questions. Okay, so first of all, I have introduced the concept that we were taught in high school or middle school, polynomial. Polynomial is like read this way, right? Fx. So fx equals to c0 is like a constant coefficient plus c1 x. X is a variable or a determinant plus c2 x squared, blah, 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 c n minus 1, x to n minus 1. So the degree of this polynomial is like n minus 1, right? It's a polynomial. Okay, it's called a univariate polynomial because we have only one variable. Okay. So polynomial is the core concept inside the SNARK framework. Why it is so important? Because we can use a polynomial to encode a vector. That means we can encode a very long, for example, 1 million size of a vector. Each element, each of the component of the vector is a finite field element. So we can write like this. F belongs to it's a finite field. Okay, like this way. The F is a finite field. For simplicity, we like the F is a prime finite field. So it means there is a P. P is a prime number. And then inside a finite field, that the addition, multiplication, and division, those operations are closed with respect to the set of finite field. So here are the basic concepts. Any questions so far? So the coefficients of this polynomial are elements from this field. Okay. Sometimes people ask me, so what is finite field? Okay. Anyone who know what finite field is, please use your hand. No? Okay. Okay. Finite field is like, for example, F2 is a binary field. It's a set with only 1, 0. Or F7 equals to a set from 0, 1, blah, 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 all the way to 6. So basically, we can mode an integer, z, mode p. So the result will be F7, right? Because every integer mode p, we project the z into a smaller set. It's a finite set with finite elements, right? From 0 to 6. Okay. But for example, -1, -1, mode 7. So what would be like -1, right? But okay, where's the -1? Where is the -1? But here is -1 because it's 1, 2, 3, 4, 5, 6. Okay, so it looks like a circle. Actually, it's a cyclic group. In abstract algebra terminology, is like a group. But we don't bother with that concept. F7 is from 0 to 6. Here we just assume that, okay, use a pretty small finite field. So what property we get from the finite field? So every a b from the finite field 7, and a plus 1, a minus 1. Sorry, a plus b, a minus b, a times b, a will also belong to 7. So 7. So the prime field has such very nice property that if we do addition, subtraction, and multiplication, and also division, well, we also get a result inside F7. So it's arithmetic closure. Okay, so it's very good. So here is a fx. So actually, one fx can encode information, right? We can put the information into one polynomial. For example, here, C0, C1, C2, all the way to, say, n minus 1, we have n numbers, right? N numbers. Then we put it into one polynomial. Then basically we can say that, okay, we compress the information into just smaller values, so f. So f. So polynomial y is the reason why we can generate smaller, very small proofs, just because we put a very long, encode a very long vector into one polynomial. Then the verifier can challenge some random number. For example, we have two polynomials, right? Two polynomials, f and g. Their size are same. So the verifier can challenge one random number r, and the verifier can reply fr and gr. And the verifier just verify if fr equals to gr to make sure if f and g are same, right? So it's a random challenge to prove that, okay, if the two polynomials are equal or not. So, okay, you can say the communication is smaller, it's constant size, right? The verifier challenge a random r inside fp, f7, and then verifier, we assume a verifier will, we assume prover reply the two values honestly. And the verifier can easily check the two values if they are same to get the statement if f. So they want to prove that fx if equals to gx. But here f is 1 million long information, right? And g also has 1 million long, 1 million elements inside. So we just challenge one point to prove a 1 million vector if you use to 1 million vector. So that's the basic idea, that we can compress a very big computation into a very small proof. This is the heart, the core of where the power of the proofs come from. Okay. Okay, any question here? It's called this is called Schwartz lemma. You can ask AI for more information. Schwartz lemma. Okay. It's called polynomial testing. Okay, just the one challenge to test if two polynomials are equal or not. Okay, it's too basic. Right? It looks so easy. Right? It looks so easy, but yeah, we can use this one, many times to build. Okay.
Yeah, so I have a question.
Huh?
Essentially, you think that the whole point of polynomial is
Sorry. Huh?
He told us the whole point of the polynomial is to squeeze one big computation into, and so the whole proof being submitted
Sorry, last sentence. I didn't get.
fx and the gx,
Uh-huh.
those are now essentially the proofs that are submitted for the verifier to verify.
Okay, that's a polynomial.
Yeah, I'm asking fx and gx, that is the proof that is generated by the prover that is now.
You mean the polynomial themselves?
Yeah.
Okay. Okay. Here, I assume that the prover and the verifier, okay, it's not a complete proof because now we have to trust that FR and GR are correct. But it turns out the prover can cheat at this step. So we need more machinery to help verifier to ensure that, okay, the two values actually are exact evaluations of the two polynomials. So it's not a completed protocol yet. Yeah, I will add more stuff into it to make a polynomial command protocol. Yeah.
But then the whole polynomial is not being sent to the verifier, right?
Oh yeah. Verifier only has the commitment of polynomial. We use the square bracket to specify the commitment of. So this one generally will be constant size. It'll be small. It is small, very small, and a G commitment. And because the verifier can hold the commitments of M and G to make sure that the prover cannot cheat at this step. Now, verifier can additionally check if these two evaluations, if they are correct according to the commitments the verifier get first, beforehand. Yeah. Does it make sense? Yeah, okay. But here, the basic intuition that I want to say is that, okay, there is a Schwartz-Visible lemma who can ensure that, okay, the verifier can just test one point to ensure that, okay, two very long vectors are equal or not. Okay, this one is very powerful. Okay, but we'll still do more work to make this protocol sound to ensure that, okay, the prover cannot cheat. Yeah, okay. Polynomials. Here, okay. There we have another way to encode. Okay, here we encode C0, C1, C2, all the way to C minus 1 as the vector, to encode that vector, compress the vector. But still we have different approach. They call it the Lagrange interpolation. The fx can be written this way, A0 plus, times L0x plus A1 times L1x plus A minus 1 Ln minus 1x. So where the Lix set are Lagrange polynomials, that A1, A0, A1 all the way to A minus 1 is also the information or vector you want to encode, but in different way. But here there are coefficient of, okay, here we have the x k to k, we call it a monomials. But here they are Lagrange polynomials. So for those who studied like linear algebra, sorry, not linear algebra, like algebra courses, if you took that course, we can say, okay, there are different bases for the same vector space. So yeah, basically we can have the definition. So from Wikipedia, you just ask AI. So, but here you only the concept that you have to know is that okay, we can encode the vector using different approaches. Okay. But now we have two. Basically, actually, we have another different ways to encode a vector into a polynomial. We basically have multiple approaches. But here, we just compare this one as a coefficient of monomials, or the vector as coefficient of Lagrange polynomials. Okay. Here, any question here? No, it's okay? It's okay? Okay, yeah. But right now, for Sumcheck, we need multivariate polynomial. Sorry, polynomial. So now so that's the reason why this part is slightly more difficult to understand than this part, because we learned that in high school. But here, multivariate polynomials, things getting different. For example, a polynomial like this way, fx0, x1, about to xk, k minus 1, sorry, k minus 1, we have basically k different variables. Okay, polynomial. Okay, for a unitary polynomial in a high school, we can learn that, okay, we can imagine that for each polynomial we have actually a curve. You can imagine that the curve in the head to understand what polynomial is, right? It has a geometric correspondence. Now it's a curve over a plane xy. The coordinates plane. Then for example, the y equals to x squared. Or basically, we got the how to say it in English, hyperbola, something like that. 抛物线, I don't know how to say English. Parabola. Okay. Yeah. Then for this encoding, actually we write this way. Well, I have an x, y coordinates plane. We choose a domain here as the omega 0, omega 1, omega 2, omega n minus 1. And then put a0 here, a1, a2, for here, n minus 1. Then we interpolate this n points into a curve, something like that. Okay, this also is fx. It's correspondence of fx. But here, if we use multiple varied polynomials, we have to imagine a high dimension space. It's much harder to imagine, right? It's a curve or a surface or a very complicated object in a high dimension, for example, 4 dimension, for example, k dimension space. But that's the reason why Sumcheck is not that easy to use, because it relies on the multivariate polynomials. But trust me, it's not that hard to understand. If just follow step by step, if you don't follow, just interrupt me, okay? Okay, multivariate polynomials. Here, for simplicity, we introduce one special family of multivariate polynomials. We call it a multilinear polynomial. Multivariate linear polynomial. Okay, whose geometric correspondence was much easier to imagine in your head? Still, it's a multivariate polynomial. So, okay, let's write it like this way. Let me give you a very simple example. We have three variables, x0, x1, x2. Okay, we can write it this way. C0 as a constant coefficient, and C1, x0 plus C2, x1 plus C3, x0, x1 plus C4, x2 plus C5, x0, x2 plus C6, x0, sorry, x01, oh, sorry, x2, x1, x2, and plus C7, x0, x1, x2. Okay. Okay. Any idea about this form? Okay, looks intimidating. No? Okay, this is called a multilinear polynomial. Okay, it's kind of a special form of special multivariate polynomials. Why? Because in each term, the largest degree of each for each variable cannot larger than 1. So, for example, for this term, x0, the degree of the x0 is only 1, only 1, and only 1. For this term, the degree of x0 is 0. The degree of x1 is 1. The degree of x2 is 1. So that's why we call it a multilinear polynomial. Okay, this polynomial is another way to encode a very long vector. But here we use 3. For example, if we want to encode a 1 million element, then we have to use log n number of variables. So the log 1 million is 20. So basically, we can use 20 variables to encode a 1 million long vector. Okay, this way we just use one variable, but here we have to use 20 variables to encode a 1 million long 1 million long vector. Okay, you may ask what the motivation is. Why we use so complicated form? Okay, this form is much more clear, right? Much clearer. But this way looks intimidating. Because if we have 20 variables, basically we are working in a 20-dimension space. Okay, but turns out, okay, this way we'll have more machinery to work on. Why? Because it's an intuition that because we're working in a high dimension space, then we can decrease the dimension for each time we decrease one dimension. Like we fold the high degree dimension space, step and step, into a low dimension space. Okay, and we can introduce more interaction. For each round, the verifier will raise a new random number. Then both the prover and the verifier can fold the high dimension, for example, a 4-dimension space into a 3-dimension space. Fold it into half. We got a smaller space. And then in the new round, the verifier will raise another random number, and the prover can fold it into half. For after logarithmic rounds, the high dimension space will be folded into one point. Then we just check that point, if the point is correct or not. Then we can get things done. And the work of checking one point is much, much simpler, right? So that we use the multiple variables because you can use the interaction. So let's rephrase the intuition. We can fold the high dimension space step by step by step, and all the way to one point. And then so after logarithmic rounds, we can easily check the final result. That's the way we can compress a proof of a very, very large computation into very smaller object, a folded computation. Now we check using very easy protocol. Yeah, this is basically intuition. So, but right now we just okay, we just put it here. So. It's called multilinear. Why? Because for each variable, we can substitute, for each variable into some, using some element. For example, we put A0, A1, and then left the three variable as variables. So by substitutes the first two variables in with some constant number, then this polynomial will be a linear polynomial. Or we just leave the middle, the second variable, leave it alone and instantiate or substitute x0, x2 with a0 and a2, then we actually got another linear polynomial. So at every dimension, this polynomial is a linear polynomial. It's one univariate polynomial. It's a linear polynomial. So what is called a multilinear? Because this polynomial, it's geometric object in the high dimension space. From each angle, it's a line. It's a line, a straight line. The straight line will, very easy to do something, the math, the matrix multiplication, something like that. So make the linear, which is a linear rise. This way, it's a much complicated curve, with a lot of curves, right? But here, in a high dimension space, it's like from each point of angle, we just say a line. But from a different angle, we see different lines. But actually, they are lines. This 1 million long vector can be seen as a composition of many lines. Okay, it turns out for each step, we just we prove the property of a line instead of a higher order curve. That'll be much easier. Yeah, that's the reason why. Okay, this approach is not easy to understand, but actually, if we take a closer into each step, it is very, very easy, simple. Okay.
Question, so you can see if I understood. So first, when we were talking about having this very big dimension,
Mm-hmm.
and with the verifier gets a random number, and then it sort of folds in.
Yeah.
That's how multilinear.
Yeah.
And then connecting back to when we were talking about the polynomial commitments.
Mm-hmm.
So when I asked you how many rounds the prover verifier, so what that means is examples with the SNARK polynomial commitment, the 0 log n, right? So that's how many times verifier will send a random number and then it folds.
Yeah.
And then up to the point to get to the point where we're talking about
Yeah.
MK.
Yeah. Yeah. Yes. Yeah. Yes. Okay. So so now the people working in this sector, they prefer to multilinear polynomial commitments instead of linear polynomial commitment because we basically have more flexibility to prove something. So, yeah, okay. Okay, this one, we encode the coefficients of monomials like this way in univariate polynomial sector. But we also have some correspondence to this Lagrange polynomial part. So that means we can also build Lagrange interpolation, looks like this in the high dimension space. Okay, we can write things like this. A0, the EQ 0, 0x1, x2, plus a EQ x1, blah, blah, blah. Okay, here we just use 7. Okay, 7. Because 7, yeah, which is 7. Just we can represent this vector using a 3D space, because 3D space is easy to imagine. X0, x1, x2. So okay, I will show you the definition of this one. So EQ0, x1, x2, x2. 1 minus x0 times 1 minus x1, 1 minus x2, and then EQ1, x1, x1, x2, x0 times 1 minus x1, 1 minus x2, EQ3. What? Okay. Okay, let's run EQ4, 0, x1, x2. So, sorry. So, sorry?
Yeah,
What?
The next workshop, we still have the next workshop, the 4 and the 45.
Oh, another workshop?
Oh, yes.
Okay.
But we can,
Okay. Yeah, we can continue tomorrow or something.
yeah.
Okay.
Okay.
Okay. Oh, another. Okay. Sorry for that. Okay.
Really
Okay.
yeah.
Another workshop.
And
Okay.